Here's the solution to quiz number 7 for ECE 320 electronics. The first problem is a DC to AC converter. If I had a DC to AC converter with this output, I've got a bunch of harmonics. If all the energy is in the first harmonic, what's the total energy in the signal, energy in the first harmonic, and the efficiency, meaning how much of the energy is in the first harmonic? Well, this is actually what you want. If all the energy is in the first harmonic, the energy is 1/2 the cosine squared plus sine squared their amplitudes, 110.5 watts. The total energy is the sum of all the harmonics, 110.5. Energy in the first harmonic is 110.5. The efficiency is the ratio, 100% efficient. That's really what you want. Problem 2 says, suppose instead you have these numbers. Well, the energy in each harmonic will be the 1/2 of cosine squared plus sine squared, 1800 watts, 12.5 watts, 50, 98, 12.5. Add them all up, I get the total energy in the signal, energy in the first harmonic, and the ratio is the efficiency. So this would have 91% of the energy in the first harmonic. The higher harmonics just cause the AC synchronous motors to vibrate, getting dissipated as heat. Problem 3. Given a circuit, find the differential equations that describe the circuit. Well, the trick here is for inductors, V equals L di dt. For capacitors, I equals C dV dt. So if I start with the inductor, the voltage across the inductor is V0 minus V1. That's L di dt. For this capacitor, use conservation of current. I1 is I3 minus this current minus that current. All the excess current has to be I1, or current in equals current out, conservation of current. That says that I1, which is C dV dt, 0.01 times the derivative of V1, is I3 minus V1 over 50 minus V1 minus V2 over R2. For the second capacitor, conservation current says current in equals current out. This current must be I2 plus that current. Current from the left is V1 minus V2 over R2. This current is V2 over 60. Anything left over must be I2. And that's equal to C dV dt. So here's the differential equations that describe that circuit. Problem 4 is a 4-diode version of a semiconductor relay. So what's happening is if I have a sine wave coming in, that's a 30 volt peak sine wave in this case. I've got a sine wave that looks like this. I've got a firing angle of 24 degrees. So at 24 degrees, the diode turns on. I follow this waveform. With only 4 diodes, I have to stay on until the second set of diodes turn on. 24 degrees past 180. Then the second one turns on, and I get this waveform. So that's the waveform at V1. The DC value comes from this formula. Firing angle is 24 degrees, saying that the average is 16 volts. By voltage division, the DC voltage at V2 is 30 over 30 plus R1 times V1, and for my circuit it was 13.7 volts. So there's the DC voltage. For AC voltage, let's do AC in red. The AC voltage roughly is this part. It's the peak-to-peak voltage. That'll be the peak going past 180 down to here, 24 degrees past peak. That gives you 42.2 volts peak-to-peak. So this is 42.2 volts peak-to-peak. That's the AC voltage. Define the voltage at V2. AC voltage at V2. Find the impedance of the capacitor, put these in parallel, do voltage division. That times the input gives you the voltage V2, 4.9 volts peak to peak. So this is 4.9 volts peak to peak. So that'd be the analysis. That's the answer for this problem. Problem 5 is the same problem, but I add a diode right here. What that does is, for the waveform, and we've got my sine wave coming in. At 24 degrees, it turns on, and I get this waveform. When they're both turned off, this one turns on. And then I get a rectifier. Kind of does this waveform. The minimum is minus 0.7 when this diode is turned on. The peak is 30 minus 2 diodes, whatever that is, 30, 29, 28.6 volts. So the DC voltage then is the average. In this case, the average is roughly the peak minus 1.4 plus 0.7, giving you the peak minus 0.7, 29.3 over pi, times 1 plus the firing, cosine of the firing angle, minus 0.7. The DC voltage is roughly 17.14 volts. Same as before, use voltage division to get the voltage of V2, 14.69 volts. The AC voltage is this distance. That's the distance from 28.6 to minus 0.7, 29.3 volts. And just like before, do voltage division, find the impedance of the capacitor, put these in parallel, do voltage division times the input. The input in this case is 29.3 volts, giving you 3.403 volts peak to peak. So there's the answer for problem number 5. The last problem is a design. Find the firing angle, find C, so that this is 10 volts DC, 1 volt peak to peak. Now to start out, if this is 10 volts DC, find the DC voltage at V1. This is 5 ohms. Again, depends upon your birth date. This has to be 30 plus 5 over 30. This has to be 11.67 volts at DC. From the formula for the DC voltage for a semiconductor relay AC to DC converter with only 4 diodes, solve for the firing angle, you get 46.828 degrees. So again, what the waveform looks like, I've got my sine wave. I turn on at 46 degrees, which is right about here, and I go 46 degrees past 180. So that's what the waveform looks like, and repeats. So the DC voltage was right here, 11.67 volts. The AC voltage is your peak to peak. It goes from this guy up here all the way past 180. That's your V1 peak to peak. That'll be 30 times 1 plus the sine of the firing angle, 51.8 volts peak to peak. The voltage at V2 is going to be, well, to find C, let's assume this isn't there. I've got a voltage divider. I can find out what the V2 is for the AC part. That's going to be R1 over R1 plus R2 times the input, 10 volts peak to peak. I want it to be 1 volt peak to peak. So if this is 10 times larger than it should be, C needs to short out this capacitor. C needs to be 10 times smaller. It needs to be 3 ohms. So find C so that 1 over j omega C is 3 ohms, or 2.98 ohms. Omega is 754 radians per second. Solve for C. C is 444 microfarads. So that would be the design for your semiconductor relay to produce 10 volts out and 1 volt peak-to-peak ripple. That's quiz number 7 for ECE 320 for spring 2022.